Hello students, welcome to the EPG Pathshala. I am Dr. Sanjay Kumar Chamoli from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about a module, Basic Nuclear Properties, from paper Nuclear and Particle Physics. So students, let us see what we are going to learn in this module. The knowledge of basic nuclear properties, the importance of nuclear properties, the experimental ways of determining the nuclear properties. Now basic nuclear properties. There are quite a few basic nuclear properties associated with any particular state of the nucleus. What are those basic properties? The charge on the nucleus, Q, which is positive equivalent of Z number, that is Q is equal to Z into E. So charge is the first basic property, and the mass of the nucleus, which is represented by M. Various kinds of masses are defined for nuclei, like absolute mass, relative mass, binding energy, etc. Third important property is size and shape of the nucleus, which is represented by R. So R is given by R is equal to R naught a to the power 1 by 3, where A is the nuclear mass and deformation. Spin is another important property. Spin is nothing but the angular momentum of the nucleus. It is represented by J. So it has the two components, orbital component, which is represented by L, intrinsic spin, which is represented by S. Another important property is the parity of the nucleus. Parity of the nucleus is indicated by pi, and it tells whether the transition is electric or magnetic in nature. Another important property is isospin of the nucleus. It is represented by T or T3. It was introduced. This isospin quantum number was introduced in the nuclei, in the discussion of nuclei, just to separate between the protons and neutrons. And it was included because it was found that the interaction is same for proton and neutron. Another important property is electromagnetic moments of the nucleus, specifically magnetic dipole moment and electric quadrupole moment. Now basic nuclear properties, isospin. So in this particular slide we are going to study about isospin in the nuclei. So isospin quantum number was invented by Heisenberg to explain the fact that a strong interaction does not distinguish between proton and neutron. So it was experimentally found that proton, after going through this NP scattering, that proton and neutron, for the nuclear interaction between proton and neutron is more or less the same as between proton-proton and between neutron-neutron. So it means the nuclear interaction doesn't depend upon the charge of the nucleon. So in that way, we can consider that the proton and neutron are two states of the same particle, which is called nucleon. So to distinguish between these two states, which we are saying as proton and neutron, this isospin quantum number was introduced by Heisenberg. So mathematically, isospin T is identical and follows same rules as the intrinsic spin S. So how this conceptual quantum number isospin was realized in practice, that mathematically isospin is identical and follows the same rules as the intrinsic spin of the nuclei. The isospin component, the nucleon type, is like spin S in the Z direction, but since it is defined in a different space, as I mentioned that isospin quantum number was introduced by Heisenberg, so it doesn't really exist. It basically is defined in some different space. It's not the realistic space or real space, but it is defined in some different space, which is called the isospin space. So it is conventionally represented by the symbol T3 and not by Tz. And here on the right hand side, a small table is given in which the particles and their isospin quantum numbers are given. For example, this lambda 0 or omega, they have the isospin quantum number as 0. Proton, neutron or kaons have the isospin quantum number half. These pions have the isospin quantum numbers as 1. This lambda, the isospin quantum number is 3 by 2. So going by the different nature of the particle, the isospin quantum numbers are different. Now in this particular slide, we are continuing our discussion about the isospin. Isospin is conserved in the strong interaction, but not in the electromagnetic or weak interaction. Now, as we know that inside the nuclei, basically 3 interactions are present. The gravitational interaction is very, very small, so we can it is almost equal to 0, because the masses of the particles are very, very small. So gravitational force has no effect. But the other three interaction, like the strong interaction, the electromagnetic interaction, and weak interaction are present. So out of all these 3 interaction, isospin is conserved only in the strong interaction, but neither it is conserved for electromagnetic interaction or the weak interaction. It means in the weak interaction and electromagnetic interaction, the isospin change can happen. The strong interaction does not feel or couple to the electric charge, so the strong interaction of proton and neutron is same. Isospin operator I commutes with the strong Hamiltonian but not with electromagnetic Hamiltonian. So it means since the isospin is conserved in strong interaction, so the isospin operator commutes with the strong interaction Hamiltonian. But since it is not conserved in electromagnetic interaction, so it doesn't commute with electromagnetic Hamiltonian. That is, Hs T is equal to 0, but H electromagnetic T is not equal to 0. And on the right hand side, again a table is given where the particle and their isospin states. Isospin state is defined in terms of T and its projection T3. So for different kind of subatomic particles, basically the isospin state has been defined. So like pions, the isospin state is 1, 1. For pi 0, the isospin state is 1, 0. For negative pions, the isospin state is 1, minus 1. Basic nuclear properties, charge. Now, one of the important nuclear property is the nuclear charge. Charge of the nucleus, that is Q is equal to Z into E, is just the sum of protons which are positively charged. That is, the total charge on a nucleus is nothing but equal to the total charge of all the protons inside the nucleus. Now, second important property is charge is quantized. Charge is quantized means the nucleus can have charge only in terms of integral unit of electronic charge. For example, Q can be either 1 electron equivalent to 1 electron charge, 2 electron charge, 3 electron charge, etc. Means half electronic charge cannot be given to the nucleus. Next important property of nuclear charge is nuclear charge density. That is, rho C is equal to Q by V, that is equal to 3ZE over 4 pi R0 cube upon A, is constant in nature. What does that mean? That rho C is equal to Q by V, so where Q is equal to Z into E, where Z is the atomic number, and then V is equal to 4 by 3 pi R cube. So when we put 4 by 3 pi R cube and R is equal to, capital R is equal to R0 into A to the power 1 by 3. So R cube is equal to R0 to the power 3 into A. So rho C, when we calculate all this value for N, as for most of the nuclei, N is nearly equal to Z is nearly equal to A by 2. So when we calculate the value for a general nucleus, we found that the value comes out to around 3e over 8 pi R0 cube, Coulomb per meter cube. And all these terms which are in the expression, that is 3e over 8 pi R0 cube, they are constant. So when we put the value of these constants, the value comes out to be a constant. So it means the charge density within the nucleus is constant. And this has been proved experimentally also. The given figure on the right hand side is an indication of that, where the charge distribution is basically plotted as a function of distance from the center of the nucleus for various nuclei, like for helium, for calcium, for nickel, for samarium, for Lead, you can see that they have the region of close to the center of the nucleus, they have the region of almost same nuclear density, but away from the center the nuclear density falls off with distance towards the edges. Basic nuclear properties, charge. This slide is the continuation of the previous slide. We are discussing the charge. Now, charge of the nucleus. In the experiments, it has been seen that the charge of the nucleus can, in a better way, be represented by some analytical form, and which is the most appropriate analytical form by which we can express the distribution of charge within the nucleus is the Wood section form. Now, what is that Wood section form? It is the relation of nuclear density, nuclear charge density as a function of distance. So here the formula is given, rho r is equal to rho 0 upon 1 plus exponential r minus a by d, where a is directly proportional to a to the power 1 by 3, d is equal to 0.52 Fermi, and t is equal to 4.39 into d. Now the r, a and d, these are basically shown in the right hand side picture. So in the picture we can see that what is a, what is t, and what is d. All these things have been clearly marked here. So in this picture we can see that on the y-axis we have plotted the charge density, and on the x-axis we have plotted r, that is the distance from the center of the nucleus. And we can say that the Wood section formalism predict the center or the constant central charge density, and then the charge density decreases towards the edges of the nucleus. For a spherical, if we want to find the total charge included in the nucleus, then we have to integrate this charge density. So for a spherical nucleus, total charge is equal to Z into E, that is equal to a triple integral, because nucleus is a spherical in nature. So we have to consider the volume integral, and when we do that, so we have the basic expression is the total charge is equal to integral rho r into dv, where dv is the small element of volume. So we perform the volume integral, and the expression we got is equal to 4 pi rho 0 integral 0 to infinity dr over 1 plus exponential r minus a over d. Basic nuclear properties, mass. Now mass is, as we have seen in the previous slide, that mass is another important property of nucleus. So it tells that every nucleus has mass. So how to give an idea about the mass of the nucleus? The mass of the nucleus can be equated with binding energy on the basis of Einstein's famous mass energy equivalence relation, that is E is equal to mc square. So the energy of the nucleus and mass of the nucleus are equivalent of each other. So binding energy gives an information about the mass of the nucleus. So binding energy is equal to delta m c square, that is equal to z mp plus n mn minus m a n x z c square. What does that mean? Where z is the atomic number of the nucleus, mp is the mass on one proton, and the neutron number, total number of neutrons inside the nucleus, mn is the mass of one neutron, minus mass a n x z, means the overall mass of the nucleus. So when this binding energy expression is nothing but the difference of between the mass of its constituents minus the observed mass of the nucleus multiplied by c square. The nucleus has mass density rho. So mass density rho is equal to m by v. So when we solve this, because m is equal to, if the mass number of the nucleus is a, then a into, because more protons and neutrons are equivalent, almost equivalent in mass, so we can multiply this a number with mn, and then v can be represented in terms of 4 by 3 pi r cube, because nucleus is spherical. So when we solve all this, we come across an expression that rho is equal to 3 mn over 4 pi r0 cube. Now all these terms like 3 by 4 is a constant, mn is constant, pi r0 cube is a constant. So when we put their values, then we come across the charge density of the nucleus as equivalent to 1.82 into 10 to the power 17 kilogram per meter cube. Like the charge density, the mass density is also constant inside the nucleus. Now as m is equal to, so rho is independent of z. So it means the Like charge density, the mass density of the nucleus is also constant and is independent of A as well as Z. So this fact has been observed experimentally also, and in the right hand side picture you can see that the mass density is being plotted as a function of distance from the center of the nucleus for various nuclei like calcium, cobalt, indium and gold, and we find that to certain region near the center the mass density is uniform or constant, but after that the mass density falls off gradually towards the edges of the nucleus. Basic nuclear properties, size and shape. Now size and shape are another important properties of the nuclei, that every nucleus has some specified shape as well as size, some fixed size. The size of the nucleus is defined by either in the following two ways. It means if we want to know or if we want to get an information about the size of the nucleus, then the size of the nucleus can be obtained in two ways. Number one, by the size of charge distribution, and number second, by the size of matter distribution. And in the two pictures, it has been shown that on the picture on the left hand side, the charge distribution density is given. On the right hand side picture, matter distribution is being given. That is, matter density is being plotted as a function of distance from the center of the nucleus. Now we find that in the two pictures we can see that the behavior of charge and mass densities are more or less constant or more or less same. That is, near the center the charge and mass density are basically constant, and towards the edges the charge and mass density both they decrease with distance. Now why we basically can get an idea about the size of the nucleus from charge and matter distribution. Charge distribution is basically nothing but the distribution of protons inside the nucleus. Mass density means the distribution of neutrons and protons both within the nucleus. Now these two distributions are different within the nucleus, and why they are different? Because neutrons are feeling only the strong interaction within the nucleus, and the protons are feeling two interactions, that is the Coulombic interaction as well as the strong interaction. Because of this difference, the charge distribution and mass distribution inside the nucleus are basically little different, but their pattern is more or less the same. So we can get the information about the size of the nucleus either by observing the charge distribution or the matter distribution as a function of distance. Basic nuclear properties, size and shape. Now experimentally, the people have found that RQ is almost equal to Rm, that is equal to R for most of the stable nuclei. So R is equal to R0 a to the power 1 by 3. What does that mean? That in the experiments, people have found that the distribution of charges inside the nucleus and the distribution of mass inside the nucleus is more or less of the same order. So we can say that the charge distribution, mass distribution can be replaced by a common term, that is R. And this R basically, as we have seen in the previous slide also, that for different masses, we observed that as the mass number increases, the value of R, that is the size of the distribution, increases. So it tends to suggest us that the size of the nucleus depends upon mass number of the nucleus. So the best expression that can be related in between these two, that can be done in between these two, is R is directly proportional to 8 to the power. So it tends to suggest us that the size of the nucleus depends upon the total number of nucleons. Size of the nucleus depends upon the total number of nucleons inside the nucleus. That is, the size depends upon the volume of the nucleus. So when we try to find the expression between or a relation between the radius of the nucleus and the nucleon number, then we come across this relation, that is R is equal to R0 a to the power 1 by 3, where R0 is equal to 1.4 for me for matter distribution and R0 is equal to 1.2 for me for charge distribution for most of the nuclei, and ρ0 is the density at the center of the nucleus. Now for nuclei, radius is a very vague term because nuclei are having variety of shapes, the density distribution in the charge density distribution and mass density distribution, that we cannot define a particular value for R because the behavior is changing at every point. We define the size of the nucleus in terms of mean radius. Mean radius is equal to distance from the center of the nucleus to the point where the density falls off 50% of its value at R is equal to 0. That is, rho is equal to 0.5 rho 0. Next, we define the nuclear skin. Nuclear skin means the distance between the density, between the point where the density is 90% of the central density to 10% of the central density. So the distance between these 2 points is called nuclear skin. Basic nuclear properties, size and shape. Now, when we talk about the size and shape of the nucleus, we come across a special type of nuclei which are called halo nuclei. Now, what are halo nuclei? They are weakly bound nuclei with very much extended nucleon orbits. Means these are some special kind of nuclei in which the radius or the distribution, charge distribution is basically extended in an unusual way to very high values. Now here on the left hand side we can see a picture is given in which a comparison of the two nuclei, that is 11 lithium, or a comparison is made between two nuclei, that is 11 lithium and 208 lead. Now you can say that 11 lithium is found to have an almost same value of charge distribution, same length of charge distribution as we have found for lead 208. Now lithium has 11 number of nucleons, total number of nucleons is equal to 11, and in lead we have the total number of nucleons as equal to 208. So very small nucleus like 11 lithium has the extended charge distribution equivalent to that of lead. So we can say that, and as we have seen that, it is the distribution of two neutrons in the lithium 11 which is very much extended. So this lithium 11 can be termed as a very special nucleus, and it is termed as halo nucleus. Now charge radius of lithium 11 is comparable to that of 208 lead. Now in the second small picture, the nuclear radius of various lithium isotopes as a function of mass number is plotted. Now in this picture we can see that for lower mass isotopes like 6 lithium, 7 lithium, 8 lithium, 9 lithium, the radius is basically almost constant and has low value. But for 11 lithium, the charge distribution extends up to the value of 3.5 Fermi, so which is quite huge. So 11 lithium for this region is a special nucleus which is called the halo nucleus. And it is not only the lithium 11 nucleus which is considered as halo. Now in the further experiments, the people have seen that there are various number of nuclei which can be considered as halo nuclei. And in the right hand side picture, a chart of nuclei is given where various nuclei, means the protons nuclei, the neutrons nuclei, neutron nuclei also, 2 neutron nuclei, 1 neutron nuclei have been marked. Proton halo means those nuclei in which the protons are extended or the protons are having large distribution as compared to the central distribution. In the neutron halo means the neutrons are away from the rest of the mass. So if 2 neutrons are away from the rest of the mass, as in case of 11 lithium, we can consider it as 2 neutron halo. If only 1 neutron is extended, then it is called 1 neutron halo. In the similar way, proton halo means if 1 proton is extended, then it is called 1 proton halo. If there are 2 protons which are extended, that nucleus is called 2 proton halo. So these are basically the various ways by which we can consider the special nuclei called halo nuclei. Basic nuclear properties, magnetic moment. So we are continuing with our discussion about the basic nuclear properties. Now in this particular slide we are going to study the magnetic moment that nuclei have. In whatever state they are, they will have the magnetic moment. Now magnetic moment means every nucleus is we consider as a tiny dipole. Magnetic dipole moment due to spin is given by mu s. So mu s is equal to G into S into mu n. Going by that formula, we can see that mu s is equal to is the product of Gs, the Lambda G factor for spin component, and S is the intrinsic spin, and mu n is the nuclear magnetron, where Gs is the spin G factor and S is equal to half for protons and neutrons. For free nucleon means if we consider a free proton and a free neutron, then the spin G factor values for them are given by for proton Gs is equal to 5.58569, and for neutron Gs is equal to minus 3.8260837. For spin half particles, for spin half point particles like electron, the Dirac equation gives Gs is equal to 2. So out of Dirac's theory, all the particles which are having spin half, intrinsic spin as spin half, they are expected to have the Gs value as equal to 2. But here we can find that, or here we find that for protons and neutrons, the experimentally measured Gs values are nowhere close to this 2. So it means the protons and neutrons are not fundamental particles. For a nucleus, the net magnetic dipole moment is given by mu is equal to mu L plus mu S. Basic nuclear properties: spin. For a given nuclear system, J is always a good quantum number. Now, as we are discussing the basic nuclear properties, so spin is also an important properties of nuclei. That is, every nucleus has a spin. Now, spin is nothing but the total angular momentum possessed by the nucleus. For a given nuclear system, J is always a good quantum number. It means in whatever state the nucleus is, it will always have some angular momentum associated with it. Now this J basically, for certain nuclei, depending upon the number of nucleons inside the nucleus, the spin can be half integral, or spin can be integral. For example, for odd A nuclei, I is equal to half integral. For even A, Zn is equal to odd, that is Zn and both are odd nuclei, I is equal to integral, that is spin is integral. For even A nuclei in which Z and N both are even, integral spin is equal to 0. Now on the picture on the left hand side, a vector diagram is given, and what does this vector diagram suggest is that the total angular momentum in a nucleus is basically the sum of two angular momenta in the nuclei. We know that the protons are in motion like electrons in the atom. So since protons are charged particles, so since they are in motion, so they will have their own angular momentum within the nucleus, which is called the orbital angular momentum. Similarly, protons and neutrons neutrons are also in motion, so they will have their own angular momentum, so which is called the orbital angular momentum. Similarly, protons and neutrons are fermionic particles, so they are tagged with some intrinsic spin. So when we talk about the total spin of the nucleus or total angular momentum of the nucleus, then total angular momentum of the nucleus is nothing but the vector sum of the orbital angular momentum plus spin angular momentum of the nucleus, or spin of the nucleus. In the picture on the left hand side, the vector addition or vector coupling of angular momentum L and S is given. So now in the first picture, you can see that the L is equal to 1 and X is equal to half. When added vectorially, they basically give the total spin is equal to J is equal to 3 by 2. Now in the next picture, we find that when the orbital angular momentum is equal to 1 is added to spin angular momentum is equal to half, the total spin of the nucleus is equal to 1 by 2. So we can say that depending upon in what way the orbital and the spin angular momentum are coupled, the total spin of the nucleus will be accordingly. Basic nuclear properties: parity. Now parity is another important property of nuclei. It tells that, or it means that in whatever state the nuclei are, they will have some parity. So first of all, we need to understand what is the meaning of the parity. Parity pi quantum number shows the behavior of wave function under reflection of its coordinates. Now we know that nucleus is basically a quantum mechanical system. So it is guided by a wave. So this wave basically, so a particle in the quantum mechanics is basically seen as a wave. So whatever is so it means the nucleus is also considered as a wave. So whatever is the behavior of this wave, so it will have its, so the nucleus in the quantum mechanics is considered as a wave. So it will have its wave function. So whatever is the behavior of this wave function under reflection of its coordinates, that is given by the parity, that is shown by the parity. So here parity operator, parity, it is basically an operator. So when this wave function psi r is operated upon by the parity, we can get either psi minus r or is equal to pi psi r, that is positive parity. So it means if the wave function is unchanged, if the wave function is unchanged after reflection of its coordinate, then we say that the nucleus has positive parity. But if the wave function is changed after the reflection of the coordinates, then we consider that the nucleus will have negative parity, that is pi is equal to -1. In Cartesian coordinate system, psi r is equal to psi minus r, that is where r is the polar vector. So when r is represented in terms of its component, that is x, y and z component, then psi minus x minus y minus z is equal to psi x, y, z, so even parity. And when psi minus x minus y minus z is equal to minus psi x, y, z, then we consider as odd parity. And the meaning of odd and even parities in nuclei basically are shown in figure on the right hand side. The top picture shows the odd parity, that is the behavior of the wave function is changed after suffering reflection of its coordinate. And in the bottom picture, the parity, the even parity is shown, which indicates that after the reflection of the coordinates, the behavior of the wave function remains same. Basic nuclear properties, parity. So in terms of polar coordinates, if we want to look at what is the parity, then we find that when we change the values of r, theta and phi by r, pi minus theta and pi plus phi, if the wave function is changed, then we say that the nucleus is having negative parity. But if the wave function remains unchanged, then we say that the nucleus is having even parity. As the wave function is a function of quantum numbers n, l and m, so psi nlm r is equal to psi nlm r theta phi is equal to r nl r y nl. It means the total wave function is divided in terms of its component, that is r nl, r means the radial wave function, y nlm theta phi is equal to the spherical part of the wave function. So parity is decided by y lm theta phi, that is parity is decided by the orbital quantum number L. And in the picture on the right hand side, the meaning of the change of coordinates, change of polar coordinates is shown. Basic nuclear properties, parity. So in the nutshell, if we want to see when we can consider the parity as odd and when we can consider parity as even, then we find that for L is equal to 0, orbital is equal to S, L is equal to 0 is for the orbital is considered as S orbital. We have parity pi is equal to +1, that is parity is even. Now if a nucleon is in p orbital, then L is equal to 1, so which is nothing but the orbital p, so parity is equal to -1, that is parity is odd. Similarly, if the odd nucleons inside the nucleus is in orbital d, for which we have L is equal to 2, parity is even. And if the nucleon in the nucleus is in orbital f, for which L is equal to 3, we have the pi is equal to -1, that is odd parity. For combination of wave function, the parities are multiplied. It means if within the nucleus there are many number of nucleons and they are in different states, so for combination of wave functions, so they will represent their own wave functions. So for combination of wave functions, the parities are multiplied. And so if we want to know what is the parity of the nucleus, then we need to multiply the parity of individual nucleons together, so to get the total parity of the nucleus. So two applications of parity transformation leave the system to its original state. So students, let us summarize what we have learnt in this module. The first thing that we learned is the isospin quantum number is important to understand strong interaction in nuclei. Second thing that we learned is the isospin is conserved in strong interaction. The another thing that we have learned is the different isospin T3 values indicate isobaric analog state in the nuclei. Then another thing is electromagnetic moments are important to understand the structure of nuclei. Another important thing that we have learned in this module is that nuclei have magnetic moment due to orbital motion and spin of its nucleons. Another important point is electric quadrupole moment of nuclei represent their non-spherical nature. And the last one that we have seen or that we have learned is experimentally most of the nuclei are found to be roulette in their ground states. Thank you.